and had over a decade of experience in the consultant world prior to that. And Grant, I believe, about 16 years of experience, and he had, I believe, 3 years with consultants prior to coming to UDOT. One thing that you'll find in the geotechnical division is the people, the engineers in the geotechnical division, that's where they've come and that's where they've stayed. And so we have a lot of consistency and a lot of experience within our group. And as we look at this topic, one thing that this is somewhat geared to would be those who are in the field dealing with these aspects of projects. And so if you have any questions regarding geotech issues in the field on construction sites or that involve UDOT projects, we encourage you to utilize the geotechnical division as a resource, because any of our engineers are able and willing to answer questions, to be on site, to offer help and instruction as needed. So as you get this information from Jim and Grant, keep that in mind. And if you're involved with a project and someone you're working with has questions or needs help, I would encourage you to contact our group, and we'll help as much as we can. So with that introduction, short introduction, I'll turn the time over to Jim, and he'll begin with the topic of MSE walls, and then I believe the balance of the time will go to Grant, and he'll focus mostly on driven piles. But again, anytime there are other questions regarding geotechnical issues, whether it be drilled shafts or other foundation types, please utilize the geotechnical division as a resource to help you. So go ahead, Jim.
Thanks, Keith. Grant and I were very excited to give this presentation today and hope it's useful to many of you. We're going to do it in tag team approach. I'm going to focus on MSE walls, on the construction and inspection aspect of MSE walls, and then Grant will cover pile driving. So throughout my presentation, I'm going to show some examples of less than adequate MSE wall construction, but I thought I want to start off with a good one here, so nobody can say, hey, you're just showing us all the problems. Okay, so we can build good MSE walls here at UDOT. Here's a picture of one. Maybe some of you recognize this one. Yeah, we don't use these shapes anymore. It's pretty nice. Cruciform system. I don't know why we don't do these anymore. But so nobody can accuse me of not saying we can't build good walls here. I'm going to start off by talking about our special provisions specifications, and that will give me a good lead-in for showing you some examples later on. We developed these special provision specifications, 10 of them, several years ago, but we continue to refine them. And so these are going to be available upon request from the Geotechnical Division. And I've been serving as a focal point there, so you can contact me by email or by phone. And because of the fact that we're updating these constantly, we wanted to have a little bit of control on when we can disseminate these out to everybody. And so the basic premise of our MSE wall construction specifications is that we have an approval process, a pre-approval process for our wall systems. And we currently have 17 total wall systems approved here. I've colorized these in accordance with the wall type. And so you see the first 5 systems are panel walls with metallic reinforcement. This is by far our most popular wall system that we build in the state of Utah, and I think probably around the country too. And so we have these 5 MSE wall systems, and each block that I've colored are listed in order of chronology of when they were approved on our list. Number 6 you probably can't see real well, but that is our only approved wall system that's a panel wall with geogrid reinforcement. And there's some advantages to using that too, but I won't focus a lot on the design aspects today. And then in the blue you see our MSC block wall systems. The first one, though, is the only one that is a block wall system with metallic reinforcement. We currently have one system there, Key System 1, which, by the way, they have a booth out here on display. And then the other ones are block walls with the geogrid reinforcement. And then we come on down with 2 approved systems, and these are fairly recent. These are permanent wire-faced MSC wall systems. So they have reinforcement, and they're intended to have a permanent wire-faced system. And there are some applications where they just won't tolerate the aesthetics of a wire-faced system in a permanent application, but in some other ones they will. And then we have, lastly, a PMG wall system. Stands for Prefabricated Modular Gravity Wall. And that's not an MSC wall. Up. That's not an MSC wall per se. That is designed to be a gravity or semi-gravity wall system. And so we've occasionally seen those be used here at UDOT. Now, as far as design requirements, I just wanted to briefly mention that we have 2 different levels of seismicity that we design for. We have the 3% event, which for those of you not familiar with earthquake, that represents the bigger earthquake. The longer frequency, the lower probability means it has a higher acceleration. So that's the higher degree of acceleration that we design for, and we use that when we're within 50 feet of a bridge abutment, or sometimes more if we have a larger bridge with softer soil conditions. But nominally we say within 50 feet of the bridge abutment, we need that higher acceleration. Whereas away from the bridge and for all other walls, we only require the 7% probability event, which is usually significantly less earthquake acceleration than the 3% event. And for you inspectors and REs, you'll notice that on occasion where you have a bridge, you'll see the reinforcement is longer in those areas, or sometimes maybe there's more reinforcement in that 50-foot proximate area to the bridge abutments. We adopted vertical spacings, maximum vertical spacings of the reinforcement several years ago. We originally had it a little bit tighter. We had it, I think, 24 inches for the vertical spacing on most of our MSC walls, but we relaxed that to 30 inches because some wall companies, panel wall companies, like to use 5-foot high panels. And so 30 inches, you get 2 layers for a 5-foot high panel. And that seems to be the norm around the country also. But for 2-stage walls, we want a little tighter spacing, and that came as a result of I-15, Salt Lake, where we had a lot of bulging seen in some of the first wire-faced phase of these 2-stage wall systems. And so we adopted that 24-inch maximum vertical spacing for 2-stage walls. I won't talk much about these design factors. These are stipulated by the project geotechnical engineer for your particular project. I will note, though, the factored bearing resistance is a very important factor, and it's important for the oversight people to make sure that the factored bearing resistance is greater than what the MSC wall company requires. If it's not, then they have to do something geotechnically to improve it, so it is. And so that's something that we watch quite often. On acceptance, we, back in 2005, 2006 era, we were quite disappointed and frustrated that we weren't getting a lot of our MSC walls constructed properly. They were significantly out of tolerance. The tolerances that we used back in the early days were those given to us by Federal Highways. And I'll talk more about those in detail later. But we were quite frustrated, and a lot of times the structural engineers, the wall companies would say, well, structurally it's adequate, but we would say, yeah, but it doesn't look good. You know, if the alignments aren't good, horizontal alignments, the levelness aren't good, then it's a problem for us. And so we adopted these non-conformance criteria for the acceptance, and we modeled these after the low concrete strength pay factors, price reductions. And so we modeled their approach there. And so we have 2 of these. The first one here, we call it for select backfill. If the select backfill does not meet the chemical requirements, then we have reduced prices assessed to them. And they may be allowed, as it says here, all the way down to a pay factor of 0.5, which means they're going to cut off half of the funding for the entire wall. So that's a significant item. And then we also have out of tolerance for the wall facing elements. And this applies, again, for the entire wall. And again, it's a maximum, the lowest pay factor is 0.5, so that's a maximum 50% reduction. In this particular case, even if you're in this realm of the 0.5 pay factor range, then we require that the wall company issue a letter saying it's still structurally adequate. So we still want to make sure it's structurally adequate, but even if it is, then we have the ability to assess this substantial financial disincentive to them. And as I'll explain here later, these pay factors are applied to the entire wall for each one of them, or a segment of wall that you're dealing with that's representative of the situation, and only the most critical of the pay factors apply for that system. And so now I'll jump ahead to the MSC wall backfill criteria. This comes in the table 1, and I'm again talking about our main MSC wall specification called Retained Wall Alternate Systems, which is 2831S supplemental spec. And so these are based, as I've shown here in the columns, on the number of tests that were performed. So if you have 1 test, average of 2 tests, 3 tests, and so forth, then it is tabulated based on these different factors on the left column. Resistivity is a very common indicator for the chemical requirements of MSC backfill for metallic reinforcement. And then pH is also a good indicator. Chlorides is a very important one. I was told by the Federal Highways head geotechnical representative that we should consider this a hard maximum. And I'll talk about those criteria here later on. And then sulfates is an important consideration also. And so I've highlighted some estimates here for us for a little comparison. We'll say, for example, on this project that, and these are deviations. These are deviations. They're not actual amounts here. These are deviations from the standard, as well as they are for Table 2 that I'll show later. But let's say, for example, that our deviations fell in this range. 1 test fell in this range, and so that would assess a pay factor of 0.95, meaning a 5% ding assessed to the contractor. And then let's go on down and say, okay, for chlorides, we were in this range, which gives us a 0.8 pay factor. And for sulfates, we were in this range, it gives us a 0.95. Okay, like I indicated, only the most strict of the pay factors apply, so that would be the chlorides. So that would be a 20% pay factor that could be reduced. Now let me back up and say these are not hard and fast values. Typically the RE, the inspectors, and sometimes the oversight people with our input will decide we're not going to assess the full value of this financial ding. They will take a percentage. They will incorporate other considerations, mitigating circumstances, how hard did the contractor work to make sure you stay within these tolerances. And particularly that comes into play more with the facing element construction. Okay, now let me move on to Table 2. This is a little bit more complicated, a little less straightforward, but our columns here are percentage of wall area. And so we have these 5 different categories that represent percentage of wall area. And the criteria we have here, 6 of them are horizontal alignment. That means in plan view, if your wall is supposed to be straight, how much does it wave in plan view from where it should be? And if your wall is curved, then it's how much does it deviate from the planned area. So it could be a deviation either way. Then we have vertical alignment. That's intended to be on any one particular panel. And I'll show you a good example of that later on in the presentation. And then we have overall plumbness. So these two often get confused. They're related, but plumbness means overall, from top of the wall to the bottom of the wall. And so they're measured similarly, but they're a different factor. Then we have levelness. How is the wall for levelness? And a lot of times they'll get the wall level to start with, but there might be some excessive settlement that occurs. And so we have to kind of incorporate the situations there as they come along. But a lot of times they get the first panels in right, which is the most important aspect of MSC wall construction, is make sure you get the first ones in right, and then they get off later on. Then we have joint width and joint offset. These are important factors too. The joint width is particularly important, I think, on the minimum level, because if you get the wall panels that are too close together, or especially touching, then you can have the potential for stress concentrations. And I'll show you another example of that too. And those can come about from excessive long-term settlement or even the design earthquake. You know, they might look fine now, but the design earthquake comes in, or even a lesser earthquake. And that jostling can cause some stress concentrations and chip and spall the MSC wall. So that's a brief overview of those. I think I might have wanted to talk about one other aspect of it. Yes, please. Thank you. Good question. The units on table 1 are the units of the particular factor here. And so, again, they're deviations. But so I've shown the units on each one of these. Resistivity is measured in ohm centimeters. So all these deviations are in ohm centimeters. pH is measured in a dimensionless factor, 7 being neutral. Chlorides measures in parts per million. Sulfates, parts per million. Okay, but on these, on table 2 for tolerances, they're mostly percentage for alignments, vertical alignment, plumbness, percentage. And for these, I've shown what the specification is. Again, these are the Federal Highways recommended, AASHTO recommended limits, but for, and levelness also percentage, but for joint widths, inches. Joint widths and joint offset are inches. So thank you. That's a good clarification. Okay, now I'll move on. Another question, Newell. Right. Good question. For those who couldn't hear that, what is the time frame when we measure these, particularly where we have a settlement concern? The contractors can say, and sometimes justifiably, that we met the tolerances as soon as we were done construction, but then it settled afterwards too. And so we're not responsible for this deviation, or especially as much of the deviation. We debated that issue, and I'm not sure if I can find it here, but we inserted the criteria that these are to be measured at the end of substantial completion. So that's our target number. And so, you know, there's flexibility again. If you've got a highly compressible site, it's settled 2 feet or more, maybe at substantial completion, it's not done, or maybe even they finished the wall 3 months ahead of substantial completion. In that 3-month interim, they came off of particularly levelness and vertical alignment. That's not inconceivable. So there's some give and go there, but the target date that we put is substantial completion on the project. If it gets out of tolerance more than that afterwards, then so be it. We can't assess a ding for that. Yes. I'm trying to see if I can see the exact point of it here, and it may not be in this one. It applies to the, of course, just to the wall facing elements. Thank you, B1, there it is. Yeah, for facing elements that are placed or underlined or that become out of tolerance from those specified before final acceptance. So that's our date there. Thank you, Ben. All right, and that is an important consideration. I think our intent was substantial completion. Uh-oh. Uh-oh. What did we decide? Yeah, it says, it says acceptance. We'll revisit that. Final acceptance, which is after substantial completion. We have to discuss that some more, I guess. And the contractual requirements change for design build versus design bid build too on that issue. So it's not a clear-cut issue, but thank you for that discussion. Okay, I'm going to jump ahead now to the 2832 spec, and let me back up and say that for all of our MSE walls, we have 3 specifications required for any one wall. 2831 is the main wall spec, that's always required. 2832 is for the backfill placement, that's always required. And then the third spec is the wall type specific spec. And so we have others that are wall type specific. The first one being 2833, which is panel walls with metallic reinforcement. 2834 is panel walls with geogrid reinforcement. And so, but for the interest of time, I'll just talk about the most common one, 2833, for panel walls with metallic reinforcement. But first I want to talk about some of the aspects of the wall construction placement that you inspectors and REs are going to be looking at. We provide the submittals in accordance with an AASHTO accredited lab. The select backfill source has to be tested ahead of time, but also we require periodic tests. So if you have a larger project, you might have to do another subsequent set of chemical tests to confirm the backfill. But we require a gradation test every 5,000 cubic yards and chemical tests every 10,000 cubic yards. And the engineer, of course, has the right anytime he wants. If he sees the material change, he has the right to order another set of compaction tests to see if the source material has changed. Talks about our density test frequency here. Every 100 feet of wall length, you don't proceed until the backfill has been passed off. And we pay particularly important attention to what the compaction is in this 3-foot light compaction zone. You don't want to compact with too heavy equipment right next to the wall face, whether it's block or MSE panels, for fear of pushing them out. So you have to use lighter equipment and oftentimes thinner lifts, so you avoid that problem. Now we come up to the gradation requirements. These are again modeled after they're exactly the Federal Highways recommendations. Both of them have a maximum 15% fines, and this is mainly for pull-out resistance. And this is oftentimes a sticking point, especially for pit run material, if they're trying to use that. For metallic systems, we only require a maximum size of 4 inches, but for geogrid, 3/4 of an inch. Why do we require a 3/4 inch max for geogrid? We're trying to be mean with geogrid people, aren't we? Very good, damage factor. And so on occasion, they just don't have a source that's 3/4 inch minus, and so in that case, we have damage testing aspects here. And that can be a little bit laborious, but sometimes it'll pay a contractor to do that damage testing and prove that the backfill that has some 3/4 inch plus isn't going to damage the geogrid reinforcement. Organic content, less than 0.5%. We also adopted the requirements of a free draining granular backfill a few years ago. That was because of the hard time we had in making sure that they got compaction next to the wall face. And here now is our electrochemical requirements. These are the 4 criteria that I mentioned before. 3,000 ohm centimeters for resistivity. The pH range for both geogrid and metallic are a little bit different. Maximum chlorides, like I said, 100 parts per million should be considered a hard maximum. And sulfate's 200 parts per million. We talk about compaction next to the wall face using lightweight equipment. We talk about how to when to backfill in front of the wall so we don't have the chance of pushing it out and an excessive erosion during construction. Our compaction is modeled after Federal Highways Method D of AASHTO 99, which is a standard Proctor, 95% compaction. we begin placement of the backfill 3 to 5 feet away from the wall face and push it out. That way we keep the reinforcement straight, whether it's geogrid, metallic. We want to work away from the wall face so we keep it straight. I'm going to skip some of these. The free drain backfill placement shows the criteria that we have for that zone. Skewing the reinforcement sometimes gets to be a problem. We follow the Federal Highways recommendation, and most MSC wall companies also have this limit of 15 degrees maximum skew angle, and I'll show you some examples of that. Okay, I know I'm getting a little short on time. Panel textures for the MSC wall panels themselves. It's important that we follow you get the wall company's construction manual. Each wall company has their own construction manual. It's important to follow those criteria also. And then lastly, I'll mention that Ray Cook and I, back on Legacy in 2001 and 2, we developed these criteria for panel acceptance when they have excessive cracking. I jumped ahead of myself, but anyway, we also require a qualified representative of the wall company be out there on the site to help train the wall construction crews. This is critical, and so much so that we codified it like this. The leveling pad, we require it to be in complete contact with the base material. You'd think that would go without saying, but I'll show you an example where sometimes it doesn't. I'm going to skip that. The wall construction company is the best entity to tell you how much to provide a positive batter during construction. They incorporate the length of the reinforcement and the type of the backfill and maybe some other factors, but they help the wall crews determine how much do you batter those initially into the backfill, and so when they relax a little bit, depending on the type of the conditions, then they'll come into alignment and they won't miss their tolerances. So look for your wall company's representative to help you with those kinds of things. Splaying reinforcement around the obstructions, there's different ways to handle that. We require that the horizontal spacing between longitudinal reinforcement not be more than 7 feet. We see big gaps of the reinforcement sometimes when they splay around piles, for instance, or drain boxes. We want to avoid those. Here's our tolerances here that we saw on the table earlier, so I won't elaborate on those, but we give some suggested measurement lengths, like horizontal alignment measured typically in 30 feet, vertical alignment typically in 10 feet, and so on and so forth. So you can look at those, and our joint widths that we talked about earlier. And here I jumped the gun and talked about our panel crack and spall repair criteria, so I won't dwell on that anymore. Okay, let's get back to our PowerPoint. Now, hide the children. We'll show you some examples of what we don't want to see. Okay, we talked about leveling pads supporting the panels here. Obviously, that's not supported continuously. That you can get all kinds of excuses from a contractor saying, you know, why this didn't matter and why we should let it go, but in this particular case, they need to make sure it's supported properly. Splaying reinforcement around obstructions. It's not appropriate in this case to be cutting these longitudinal bars, which are critical with our cross members around these piles. And also the fact that the reinforcement is touching the piles is a very good no-no. Boy can tell you that about the cathodic situation you're dealing with there. So this is an example of what not to do, what not to allow. When you have excessive settlement after construction, this was well after construction was over, a year or more on Legacy, and you have these kinds of stress concentrations with spalling and chipping. And so it's important in these aspects to make sure that you know if the settlement releases were properly done, and don't release the settlement until it's time. Grant could spend a day talking about that for us. But those are some multiple examples, and sometimes they try to minimize how serious that of a situation that is, but it's something that we want to pay more attention to. A lot of times they leave the gap widths too wide. So what do you do then? Well, you just put in some of this filler here. Yeah, nothing wrong with that. And then you just spray some paint over the top of it. That makes it look just fine, right? It'll stop the backfill, at least for a few years anyway, until that material degrades. And so that's another reason why we watch our joint widths. Acute corners on walls. Just like cliches, we like to avoid these like the plague. Not one laugh. Oh, man. But we decided that we were so frustrated with these, particularly on DB projects, that we codified the fact that they should not use acute corners less than 70 degrees and absolutely not less than 45 degrees. MSC wall companies some of them will say, well, we can still design for it, and they can properly, but there's so many other issues that come into play here. This is SR92. I come up to this site, and I saw their big old Bomag 10-ton roller coming right in here as tight as he could. You know, no reinforcement here, but he's rolling right in next to the wall panels without being reinforced there in this acute corner angle. So what are the results of that? What are the problems? Well, that's the result. More stress concentrations when things shift around afterwards. Two-stage wall are a particular challenge for us recently. A lot of times there's not enough attention in placement of the backfill on the first stage of these construction. This will remain nameless, but that's our Federal Highways representative looking over that, and unfortunately he's taking these pictures on the road with him. And so this is what not to do. Of course, it's a two-stage wall. Who cares what the first stage looks like, right? Well, in general, we care about these tolerances particularly because they're also an indication not just what the aesthetics look like, but how much care did the contractor, did the wall construction crew place during construction. If he was sloppy with his tolerances, he's probably sloppy in his compaction too, and it could affect the long-term bridge performance. Now, here's a couple of examples here. This looks like a pretty good first stage wire face wall. Pretty straight. Here's another one. That's not quite so straight. Okay, that's not really a fair comparison, you're saying. This one I'll mention, I'll give them credit. This is the Hilfiker permanent wire face wall system that they have. And if you might say that's not a fair comparison, these walls were on the same project. You know, a fairly compressible site, but that's on the same project. Vertical alignment. Here's a little example for you for vertical alignment. John knows very well what project this is. So this is what we're measuring here. If we say the vertical alignment, we're talking about each individual panel, both into the plane and out of the plane. So this would obviously fail on that, but this is an extreme example. This obviously needs to be mitigated. Can't just be left in place in that condition. Same project. Drainage is important, and all MSC walls drain well. I think this was pre our grainer backfill, our open graded backfill placement requirements. But this is an example of how the wall runoff was coming right through the joint there. Obviously not a good situation. You're increasing your lateral earth pressures on the project, so we pay particularly important about drainage. And I picked on panel walls quite a bit here. So here's one block wall example here. We've got a new rotational coming up, so I think I'll have her calculate how much a leveling pad, unreinforced leveling pad, is designed to span for an MSC block wall. The answer is it's not designed to span very much like that. So that needed to be obviously mitigated. So thanks for everybody for your attention and particularly for your help and help us ensure we construct good MSC walls in the state. They can be constructed well. And if you have any questions, I think we could ask a couple now, or we could save them all until after Grant's presentation. Whatever seems most appropriate. Let's move on then. I'm going to load up Grant's.
So while Jim's loading that up, last time that Jim and I did this together, I went first, and I didn't leave him hardly any time at all. So he's being generous at leaving me a little bit of time here, so I appreciate that. But how many here like this room that we're in? Okay, I just want to point out a couple things that are actually pretty nice about this room. First of all, if you don't like my presentation, you can just listen to the next one. And if you really don't like it, you can just walk right straight through that wall and go to that presentation. And then one other really nice thing about this room is if you need to use the restroom, there you go. Okay, pile driving, I'm going to focus a lot on the inspection part of pile driving in this presentation. There's two types of piles that we drive in Utah, H piles and pipe piles. This is a picture of H piles. It uses large equipment, a crane, leads that are hanging from the crane, a hammer, and then the piles. And then you've got the crew, you've got a crane operator, and you've got a pile buck down in the bottom of the picture. You've got the pile buck, and he's got a rope that goes up to the hammer that turns the hammer off when it's at the proper elevation. This specifications, I'll just go through a few highlight parts. I'll skip this one because it's actually on the plans. It's the, actually it's not on the plans. Okay, this spec is talking about the pile and driving equipment data sheet that the contractor has to submit prior to bringing his hammer onto the site. And that's an example of the hammer data sheet. We need this information so that the designer can run a WEEP analysis to see if the hammer that the contractor is proposing to use will actually work. If the hammer's not big enough, it won't drive the pile to the depth that it needs to be driven, and it won't verify the capacity. If the hammer's too big, then it will damage the pile. Okay, this is the information that's on the plan sheets. So basically what it says is, for example, 2.1B says meet requirements for ASTM A252 steel for either grade 2 normal strength or grade 3 high strength steel. And that's an example of something that will be on the plan sheets. It'll actually tell you use grade 3 steel, for example. Yeah. Okay, just another picture of a pipe pile up close. Okay, here's an example of a plan sheet or a pile data sheet. This may look familiar to Christine. Is it okay if I use this? Yeah. It's a little outdated because this is about 5 years old, if I remember correctly. And now the pile data sheets, the pile data information down in this box is, there's a lot more information that we provide today. But even so, the three most important things I've highlighted in yellow, and I'll zoom in on those. The three most important things for inspectors to know. This just shows that it'll show the pile size, which includes the diameter and the wall thickness. Both are important. Inspectors should measure those when they come out in the field, when the piles come to the field. This shows the notes. The important things in this that I want to point out are, it'll tell you, here's the grade 3 steel, which is a high strength steel, and it will actually tell you the strength of the steel that is required that pipe pile or H pile be. In this case, it's 45 KSI steel. So then the contractor will have certs that show, that they're called heat numbers, and it'll show what those values are. So they have to be at least what's shown here. Let's see, another one is pile tip elevations are approximate, verify at time of construction in accordance with specifications. And I'll go over that in more detail. Pile hammer requires a minimum rated energy of 60 kip feet. And that pile data sheet, that pile data form that the contractor's required to submit as part of the submittals has that information on it. And again, that is a value in order for the hammer to be able to drive that pile into that soil, whatever, at the location in the project. It has to have a minimum rated energy, and in this case, it's 60 kip feet. In the spec, under the hammer, it says rated energy greater than or equal to the value indicated on the foundation plans. I just pointed that out on the plans. Okay, so do any of you know what that is? Did I hear post? Yeah, a fence post hammer, right? Well, a fence post hammer is a pile driver. What it is it's a mass. You lift it up, you drop it, it falls a certain distance, lands on the top of the fence post, and drives it into the ground. A pile hammer, that's what a pile hammer is, actually. So here's a diesel pile hammer, and what it consists of is a ram, or it's also a piston, and it has a certain mass. Around here, the typical one is about 6,600 pounds for the ram, and the way it works is there's an actuator. Well, the crane lifts the ram up to begin with and drops it, and then as it drops, it hits this pump actuator, which is a trigger to turn the diesel pump on to spray a jet of diesel fuel into the chamber, and then when the ram hits the bottom, the diesel fuel explodes and sends the ram back up in the air. One thing to remember is there's always for every action there's an equal and opposite reaction. So what that means is the ram comes down and hits the pile. The pile's right here, so that force hits the pile. If the pile moves significantly, then the reaction for the piston to rise back up with the explosion is smaller, and so it's not going to rise up as far. But if the pile doesn't move very much, then the piston has a much greater opportunity to react when that explosion occurs, and the ram will rise higher in the hammer. So here's just a simple equation that kind of shows kind of the ideas behind it. So you've got the energy is equal to the work that's done. And so you've got the energy of the hammer, which is the weight of the ram and the distance that it falls. So the weight times the distance, that's an energy. And so that is going to equal to the distance that the pile moves multiplied by the resistance that the pile is providing. One of the important things about doing pile driving analysis, one of the things we do as a department is when they drive these piles, the very first pile that they drive, we go out and do a pile driving analysis, and I'll show you a little bit more about what that involves. But one of the reasons we do that is to make sure that the pile doesn't get overstressed. And this is a picture of a pile that's been overstressed. The pile got hit too hard with the hammer. And one thing to keep in mind is these piles have feelings, and I found that out when I took a picture of this same pile from a different angle. I noticed that the pile was reaching both arms out and letting me know that it didn't like being hit that hard. So back to the pile data information. Here's the required minimum driving resistance. So that's when we bring the PDA instruments and computer out to the site. We hook up the instruments and we measure it to see if indeed we are getting that capacity and we don't do that, well, we do that once the pile is at the depth that is shown here on the plans. There's an estimated pile tip elevation and an elevation of minimum acceptable pile penetration. So the estimated one is what the designer thinks it will go to, but like any soil profile, you might get out there and there might be a boulder or a hard layer or something that the pile gets stuck on, and then the hammer just hits it, pounds it, but it's not moving very much. Well, we don't want to overstress the pile. So the minimum is based on lateral capacity of the pile, settlement of the pile, scour, so it has to be at a certain depth for scour, and then uplift capacity. So if for some reason the pile can't get to the minimum, then the contractor has to pre-drill through whatever dense layer in order so that when he does drive the pile, then it will get at least to that minimum depth. And then the estimated is what the designer thinks it's going to go to, and if it doesn't, well, that's when we bring the PDA equipment out and we run the test to see what capacity is. And if they don't get capacity at that estimated, they actually end up having to go deeper until they get that capacity. Or the other way around. It is possible to get that capacity at a lesser depth, but that's the reason we run a PDA test, to find out. Okay, so this is the part of the spec that actually talks about the department coming out and doing PDA testing. And we do it at the first pile of each abutment or bent foundation. And then based on that information, the department comes up with what is called the driving criteria. And the driving criteria involves three things. It's the depth at which the pile needs to be driven to, the blow counts, or the blows per foot, and the hammer stroke, or how high that, or how far that hammer ram falls. So all three of those things are critical. Not one of them can suffice to indicate that the pile is okay. You have to have all three of those. So here's the equipment that we use, the instruments that we hook up to the pile. The middle one is a strain gauge. The one on the right is an accelerometer, and there's another accelerometer and a strain gauge immediately opposite. Another accelerometer on the back side. This is an H pile. So this is the web of the H pile. So there's another strain gauge immediately on the other side of this strain gauge, and then an accelerometer here and an accelerometer there. And then we hook it up to our computer and run the analysis. And if you spend too much time around some of these piles, it can kind of mess you up a little bit. So here's a pile driving record. The top just gives the pile information. The middle part is actually not filled out until the pile is already completely driven and they've cut it off. It's the plumbness and the pile location. And then here's the pile driving record, and the three things that I mentioned are shown on here. The pile depth, which is this column here, in this case 113 feet. This is the blow counts, so you count the blows, how many times the hammer hits the pile per foot. So in this case, at the very end, it was 20 blows per foot. And then the hammer stroke, which is 9.1 feet in this case. And you can determine the stroke from a saxometer. That's the best way to do it. And we actually have a saxometer program on our HP 48G and HP 48GX calculators. So we can beam those to you if you have that calculator, and you can just use that. The old-fashioned beam, remember that? The good old days. Yeah. Anyway, so there's that way. And then another way is you can actually visually see the ram if it's coming out of the top of the hammer. And the hammer's around here. I think it's about 8 feet. The one I measured the other day, as soon as you see the ram coming out of the top of the hammer, that's an 8-foot stroke. And then the ladders that are on the leads, they're right next to the pile and the hammer. Each ladder rung is 1 foot difference. So based on those two things, you can, by eye, you can easily determine within the nearest half a foot what the stroke is just by eye. So again, all three of those things are extremely important, and not one of them can be sufficient without all three of them. So in this example, okay, so the last one, it was 113 feet deep, the blow counts were 20, and the stroke was 9.1. So will this one be good enough? No. And why not? Well, the first reason is the depth. They're not deep enough, right? They need to get to 113 feet. The blow counts are fine because they're greater than the 20 that's required, but the stroke's not high enough. So you have to have that stroke because it tells you how much energy was hitting the pile, which is directly correlated to the capacity of the pile. So you have to have all three of those things. And in this case, my guess is if they would have driven it 1 more foot, which they have to do, they probably would have got the 9.1 foot stroke. So. Notify the engineer if any of the remaining piles in the foundation do not meet the established driving criteria before moving the hammer away from the area. I had a project one time where they did move it away, and we examined the information, and what we found was that not all the piles had met the driving criteria, and so they had to remobilize the crane and the hammer back onto the site, and you can imagine how happy they were about doing that. Okay, this talks about the out of tolerance piles, and I'll show a table. And if they're out of tolerance, then there's some price adjustments that have to be applied. And here's the table here. So the pile can be a maximum of 6 inches out of location and not have any sort of penalty. But if it's beyond 6 inches, then these particular penalties apply. And in addition to that, it can be out of plumb up to 2%. But if it's greater than 2%, then these penalties apply. And all the way up to this says 3%, but that's greater than the 2%, so the total is 5%. So if it's more than 5%, then the pile is rejected, and they actually have to drive another pile. Anytime they're within this table, the structural engineers need to know about that so that the evaluation can be done as to whether or not it will still work. So even anytime there's a pay factor that's applied, the structural engineer needs to be involved on it. Just some examples. This one's out of plumb, obviously, and more that are even more out of plumb. These are out of location. These are actually those same piles in the last picture, but now they're cut off. One of them's obviously out of plumb or out of location. This one is borderline to pay factor. Probably the last thing that I want to mention is when you're around the pile hammer, you're going to get dirty. I think that hammer's a red hammer, but you can't even tell because of all the oil on it. It's completely black. Whatever you're wearing, your clothes are going to be completely ruined. They'll be completely black, and that black oil will not come out of your clothing. So be prepared for that. And then be safe. Let the pile bucks do their job. Keep your distance. You don't ever get any closer than you need to. The best time to approach the hammer, if you need to, is after the hammer is sitting on the pile. And then, and again, listen to the pile buck and the workers, and if they need you to move, then move, get out of the way, and be safe. Oh, last thing, this just shows that sometimes a hammer can be very, very close to an existing bridge when you're trying to do a widening, and so don't always just look down. Be looking up and be aware of what's going on. In this case, the hammer's right up there against the bridge, and the designer on this bridge told me that it was fine because what they did is they took into account the resistance of the bridge when the hammer was hitting it, so it was okay. But so that's all I've got. If anyone has any questions regarding pile driving or MSE walls, we can take them right now. Yeah. Well, yeah, we can come anytime. The more notice we have, the better, for sure, in case we're off on some meeting or something. But that's true. I did go over a lot of that stuff very quickly, and we are more than happy to come out. And if you have a pile driving job, we are more than happy to come out. And the first pile that's driven, I mean, we'll be out there anyway to do the PDA testing, but we can come out a little bit earlier than that to kind of show you what needs to be done.
That's a good question. It's probably an involved answer, but let me first say that our main criteria for looking at out of tolerances for MSE panels is your eyeball. How do they look visually? Do the joints look too wide? Do they look too tight? Start to measure some and get a calibration of those. Do the panels look like they're out of plumb or alignment? Measure a few of those bad ones, and if you see, okay, yeah, they're out of the alignment, then you might look and see how many more you want to measure. For example, it's not too hard to go ahead and measure the plumbness from top to bottom of each 10-foot column of panels. So if you got five panels high, just measure each one of those columns. If you know that one or two of them are out that you've measured, then you better measure all those so you have a good representation of the percentage. And a lot of times that will govern. Sometimes joint width governs, but if you got a plumbness or a vertical alignment problem, usually you can find out pretty fast how bad it is and get a view of it. Other people have measured every vertical alignment of every panel. They've developed these straight edges that are calibrated so they can actually read in percentage. You don't have to do any conversions, and so they actually go ahead and measure every vertical alignment, and that's impressive, but it's not always necessary, hopefully. And so if we can get them started out right, building the panels right, then we don't have to go to as much effort in measuring these criteria.
Yeah, hopefully, kind of the idea behind that, those pay factors for the MSE wall is to encourage the contractor to build it at the best he can. And if he does that, if you measure 10 to 20% of the panels and stuff, and it looks good, call it good. But if it's like Jim said, if you'll know pretty quickly if you look at the wall and there's some problems, then yeah, you better start measuring a lot of it. So. My first thought on that is you probably have the wrong proctor, and that could be either the wrong proctor from from the information that you already have, or you may not have the information for the correct proctor, if that makes sense. In other words, you may have several proctors to choose from, and something's not making sense, and you've tried all the proctors and it still doesn't make sense, then to me what that means is you better do another proctor on that soil that you're having a problem with. You know, I suppose I'm sure there are soils that are the exception to the rules. There's always some kind of soil that is an exception to the rule. Let us know, and we'll. It could be if it's dry, yes. But the interesting thing is if you're getting density, even though it's less than optimum, it's probably going to be okay. But something like that, we definitely want to know about it, and we'll evaluate it further.
Just extrapolating that, on the other side of the equation, you can get too wet of optimum, especially on the standard proctor, and then it gets too spongy and wet. And it might technically meet the density, but then you have a problem meeting compaction on the next layer because you don't have a firm base to compact against. So if anything, we like to stay a little bit dry of optimum, especially on the standard proctor, which we require for MSE walls.
Brad, I was just wondering, what percentage of piles do you have to come back and destroy?
Based on experience or general? The question is restrike tests, how often we have to come back. Probably not very often, actually, probably 10% of the time. And what he's referring to with the restrike test is if we go out and do a test and we don't get the capacity that we need, the contractor actually has an option to wait a day, and then we'll come back and do another test on the exact same pile. And what that will do is it will allow the pile to set up, is what it's called. It'll obtain setup, and the pore pressures in the soil will dissipate in that amount of time. And then you will actually get more capacity when you do that. But that's not always the case, because there are instances where soils will relax over time, and the designer, the geotechnical engineer, better have a pretty good handle of that, because if there's any chance of that happening, then we need to do that restrike test for sure. I'm getting competition from up above here, it sounds like. So thanks. Let's hopefully if you're staying for dinner, then we'll see you at dinner. And thanks.